We're going to get into some application of the concept of sequences by looking at some real-world examples now. So now as you watch this video at 1 in the morning, it will be that much more bearable and relevant, hopefully. Okay, so let's get started. Let's start by looking at class example number 1. BP Birthplace Forest Program in Calgary enables parents to honor their children by planting a tree when their child is born. At the same time, this shows concern for the urban environment by encouraging the growth of city forests. Some of the trees which have been planted are evergreen trees, which grow an average of 12 to 18 inches per year, and the program was launched in the year 2000. So we're going to look at two different scenarios. An evergreen tree 6 inches high was planted in June 2000, and it has a growth rate of 15 inches per year. Two students were asked to determine the height of the tree in June 2011, and Joel performed an arithmetic sequence performing 621, beginning with 6, 21, and 36 as the heights of the tree. And Jenna, another person, performed an arithmetic sequence beginning with 21, 36, 51. Again, the height of the tree in inches. And what they want us to do is use the formulas in the previous lesson, so in lesson number 2, to determine each student's answer to the problem. Alright, so first of all, the formula we're going to be using is the general formula. And before I get started, if you're wondering what this nasty looking gash my finger is, I just sliced open my finger when I was gutting a coho I caught the other day. But yeah, it's pretty tender. Anyways, the formula we were using was Tn is equal to A plus n minus 1 times D. So that's term n, and that's equal to the first term plus the previous term multiplied by the difference. And we're going to be using that same formula because that's the one we learned in the previous lesson. We're going to be using that for both of these scenarios. Now remember, a formula without any known terms isn't much use to us, so before we even get to these formulas, let's write down some of the information that we have. So we know we have two different individuals we're working with. We're working with Joel and we're working with Jenna. Now first of all, Joel was using his first term as 6 inches. And the difference, they both have the same difference. The tree that they're measuring has a growth rate of 15 inches per year. So every year it's going to change by 15 with an end time for the number of terms being from year 2000 to 2011. So if we were to go, that's a period of 12 years, right, including the year 2000. So that's our number of terms, or our value of n, which would then be 12. Now with Jenna, the numbers she's using are a little bit different, right? Like she chose to start at term 1 being 21, and then she had a difference of 15, which was the same. But rather than, because she's starting a year later, she's not including the year it was actually planted. She's starting at 2001, which means her value of n is going to be 11. And so what we want to do is use these formulas to determine each student's answer to the problem. So first of all, Joel, he had 12 terms. So we're going to say T12 is equal to A plus, if I write this formula in shorthand, that's going to be A plus 11D. So T12 is going to be A, my term 1, which is 6, plus 11 times 15. Term 12 is going to be equal to, if I compute this quickly, 171 inches. Now for Jenna, she had 11 terms because she started the year 2001. And yeah, so A plus, if I write this shorthand again, 10D, T11 is going to equal 21 plus 10 times 15. So 150 plus 21, the T11 is going to be 171 inches. So we end up with the same answer, 171 inches in, yeah. So now let's look at part B. Tn is equal to the formula we used earlier. Now we want to determine the general formula for each of their, the piece of information that they collected. So if we're looking at Joel's information, that's going to be 6 plus n minus 1 times the difference, which is 15. Remember, this is just the general formula, 6, and I'm going to distribute my 15 into the brackets. So 15 times n is going to give me 15n. 15 times negative 1 is going to give me negative 15. I need to combine my like terms, so that means 6 and negative 15 is going to leave me with 15n minus 9. So the general term for his statement is 15n minus 9, whereas with Jenna, she used 21 for her first term, and then n minus 1 times 15. Again, I'm going to distribute my 15 into my brackets, so 15 times n is going to give me 15n minus 15 multiplied by 1, it will be negative 15. If I combine my like terms, 21 plus negative 15 is going to leave me, and that should be 15n there, is going to leave me with positive 6. And we have our general term for Jenna as well. Tn is equal to 15n plus 6. Now, part D is asking us to explain why the formulas in B and C are different. Well, the different values for the first term, so Joel used 6 as his first term, whereas Jenna used 21. So if you use different values for the first term, that's going to lead to different values of n when solving a specific problem. So different values of T1 or A, so that's our first term, will lead to different values of n. Now, if the tree continues to grow at the same rate, so 15 inches per year, in which year will it reach a height of 28 feet? So we want to know, when will it reach 28 feet? Now, it might be helpful if we convert this right away, since we're given a measurement of feet, which makes sense if we're talking about a tree. But since we're doing the rest of the question in inches, above in our formulas given, then it might make sense to turn this into inches. So there are 12 inches in 1 foot, which means in 28 feet, we need to multiply that by a factor of 12 to give us 336 inches. So we want to know, in what year will the tree reach a height of 28 feet? So we could use Joel or Jenna's formula in order to calculate this. So if we use Joel's information, if we plug it into his general equation of Tn is equal to 15n minus 9, then we're given 336 inches. And that's going to be equal to Tn. 336 is equal to 15n minus 9. If I want to if I want to solve for n, I need to add 9 to both sides of my equation, which will give me 345 is equal to 15n. And if I want to solve for n, then I want to divide both sides by 15. Move this up here. N is equal to 345 divided by 15 gives me 23. N equals 23. So that means in 23 years. And let's see if we get the same thing for Jenna. And since she used a different value of A, I wonder. So we're going to start with Jenna's general equation, which was Tn is equal to 15n plus 6. Tn again is equal to 336. And 15n plus 6. I need to subtract 6 from both sides to isolate my value of n. It leaves me with 330 is equal to 15n. And if I divide both sides by 15, that's going to leave me with a value of n is equal to 22. So Joel, 23 years. Jenna, her answer was equal to n equals 22 years. Now remember though that they're starting their measurement at different times. So that doesn't mean that these are actual, a different answer in terms of the year we're talking about. Joel started his counting in year 2000, whereas Jenna started her counting in year 2001. So if it takes 23 years to reach a height of 28 feet, for Joel, that means we're talking about the year 2002. Right? So for Joel, term 1 was equal to 1 in the year 2000, which means when n is equal to 23, that's going to be the year 2022, right? Because it's inclusive of 2000. Jenna, however, she started her term 1 in 2001, which means that her term 22 is going to be 2022, which means they get the same answer, 2022. Okay, so real world example. Now you know how to calculate the heights of trees as long as you know their growth rate, and provided it stays the same from year to year. Now, let's look at class example 2. Many real-life scenarios can be represented by a pattern of numbers which exhibit arithmetic decay or arithmetic depreciation. So now we're talking about patterns that exhibit arithmetic decay. But before we were talking about growth, obviously, with a tree growing, right? But now, let's see what happens when we talk about depreciation. So something that's losing, if we're talking about finance, something that's losing its value. So a printing press was bought in the year 1992. It depreciates or loses value. So it depreciates in value by the same amount each year. So 5 years after it was bought, the printing press had a value of $311,000. It had a scrap value of $2,900 or $2,900 in the year 2010. So use an arithmetic sequence to determine the amount of the annual depreciation. So we're going to talk about Tn and in terms of n, and we'll talk about Tn as the value of n years after the first year, so after 1992, the year it was purchased. So let's first begin by writing down our variables, right? So beginning with the information that we're given, 5 years after it was bought, so T5 is going to be 5 years after it was bought, the printing press had a value of $311,000, so that's term 5. And it had a scrap value of $2,900 in the year 2010. So 2010 minus 1992, inclusive of 92 is going to be 18 years. So that's 18 years later, it's going to be worth $2,900. we're gonna use a linear sequence like we did in lesson number 2. So I'm now using the general formula for this statement. So a plus 4d is equal to $311,000, and then a plus 17d is equal to 2,900. Now remember, with these general statements, we end up subtracting if we're talking about a linear sequence. So you might need to review lesson number 2 for the way I'm structuring this, but what I'm doing is I'm subtracting this equation and this equation from each other. So a subtract a will leave me with 0. 4d subtract 17d will leave me with negative 13d, and 311,000 subtract 2,900, which is calculated here, will be $308,100. Now I need to divide both sides by negative 13 in order to isolate the value of d, and d divided by negative 13 is going to be negative 23,700. So the annual, that's my difference, and that ends up being my annual depreciation. So every year it's going to depreciate by, so it's going to lose a value of $23,700. So part B, we want to find out what's the purchase price of the printing press. So how much was it actually purchased for? So let's go back to our first equation. A plus 4d is equal to $311,000. Now the reason I am doing this is because now that I know what the depreciation is, I can use my depreciation to solve what my first term is, first term being a. So I could use either one of my equations, either a plus 4d equals 311,000, or I could use this one here, a plus 17d equals 2,900. So either one of those equations are going to work in this situation. So a plus 4 times negative 23,700, I got that from my above calculation, and that's equal to my my value at 5 years. So 23,700 multiplied by 4, that's going to give us negative 94,800, and that is equal to $311,000. And if I want to solve for a, then all I got to do is add 94,800 to both sides. So 94,800 plus 311,000 is going to leave me with $405,000, or 405,800. So this is not the initial value, right? This is just ends up being term 1. So that's the value at the end of term 1. So to find out what the actual price was that we bought the printing press for, we have to add another depreciation amount. So the purchase price is going to be $405,800 plus $23,700. That gives us $429,500. All right, last problem. This one is pretty straightforward. So if you don't have a problem with what I've done so far, then you should be able to get the rest. But if so, then you might want to continue watching. So we can relate arithmetic sequences to linear functions over the natural numbers. And so let's look at this example. We have a pile of bricks arranged in rows. There are 28 bricks in the first row, and the number of bricks in each row is 2 more than the previous one. So we know that in our first row, and we want to complete this table and then plot this information on this graph. So in the first row, there are 28 bricks. And we know that the number of bricks increases by 2 more the previous row. So if I have a specific row number, this is going to go up by 1 each time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, and it goes up by 2, 30, 32, 34, 36, 38, 40, 42, 44, and 46. Alright, so here are my ordered pairs, and now we want to plot this information on our graph. So when we're at 1, we have a total of 28 bricks, and we know that that increases by 2 each time. So we're going to go up until we hit 10. So here we have a linear relationship, and so we can circle linear relationship. Now determine the range, if the range is an arithmetic sequence. Well, it is an arithmetic sequence because our first term was 28, so A was equal to 28, and we went up by a difference of 2 each time, and that was a constant change of 2. What's the domain of the relationship? Well, the domain, our x values are, we have a set of natural numbers, so up to 10. So say the domain is equal to, well, goes from 1 to 10 essentially. And if we want, we could talk about it in interval notation or set notation, what you learned about in grade 10. So we would say x is an element of real numbers such that 1 has to be less than or equal to x, or x has to be greater than or equal to 1 but less than or equal to 10. If you're finding this confusing, don't worry, we're going to talk about it more as the year progresses. Why does the graph not have an intercept on the vertical axis? Well, you can't have a row number 0. It's just, yeah, you can't have 0 rows and then have a certain number of bricks, so that's why that's not included. And now we want to write the equation for the number of bricks in a row, so any row n. So remember just our standard equation, Tn is equal to A plus n minus 1 times d, where n is going to be equal to, well, A is 28 plus the row number, which was n minus 1 times 2. And now all we got to do is distribute that into our brackets, and we're left with, Tn is equal to 28 plus 2n minus 2, or Tn is equal to 2n plus 26. And there we go.